In this exercise, we want to practice line integral FDR over some curve C. In this case, the curve C will be the bottom half of the circle with radius 1 and center 1, 0. And we will write 3 different parametrizations of the same curve and hopefully to get 3 equal results. By this exercise, we want to show that the line integral is not dependent on the particular parametrization. Each curve has infinitely many parametrizations, and if we change the parametrizations but keeping the orientation of the curve, then the result of the integral does not change. This can be explained physically. If you move some particle in some field, then if you change the speed, how fast you move in individual portions of the path of the journey, it does not change the work that you do. Okay, if we have a unit circle with radius 1 and center origin, then the equation is x squared plus y squared is equal to 1. If we shift the center from origin to 1, 0, then this can be described by x minus 1 squared plus y squared is equal to 1. This is the equation of the entire circle, and we will just consider the bottom part. That means we will work with y less than or equal to 0. We can simplify this a little if we expand this multiplication to get x squared minus 2x plus 1 plus y squared is equal to 1. We can subtract 1 and we have x squared minus 2x plus y squared is 0. Or we can write it in the form x squared plus y squared is 2x. We will use this form a little later. Or we can express y squared as 2x minus x squared. And we can solve for y to get the first possible parametrization. X is t and y is minus square root of, and we replace x with t, and we have 2t minus t squared. T is x, so x runs from 0 to 2. Or t runs from 0 to 2. So this will be the first possible parametrization of this curve. We write minus because we want the bottom half, because we have the condition y is less than or equal to 0. Another natural parametrization would be using the trigonometric functions sine and cosine. For this circle, x is cosine of t and y is sine of t, and when it is shifted, then x is 1 plus cosine of t and y is sine of t, and in this case t, if it runs from 0 to 2 pi, then we make one whole term, but we are interested only in the second half of this whole term, so we don't start with t at 0, but rather at pi, and we go up to 2 pi. And this corresponds to this orientation along the curve. Well, and we will consider still another parametrization. There are infinitely many of them. We will consider a third parametrization. Let's call it C. And that will be x will be fraction 2 divided by 1 plus t squared, and y will be fraction 2t divided by 1 plus t squared. Well, it's far from obvious that this is a parametrization of this circle, but it is easy to check. If you compare, if we evaluate x squared plus y squared, hopefully getting 2x, then we have x is this fraction, so we have 4 divided by 1 plus t squared, square of that, plus y squared is 4t squared divided by the same denominator. But if we bring to the common denominator, which is the same, then we have 4 plus 4t squared. But then we can factor out 4, and we have 4 times 1 plus t squared divided by 1 plus t squared, square of that. And we can now reduce 1 plus t squared, and we have 4 divided by 1 plus t squared, which is 2x, you see? 4 is 2 times 2, 1 plus t squared is here, and 2x is here, so it satisfies this equation, which is equivalent to this one. So this is, again, another possible parametrization of our curve. Okay, let us use these 3 parametrizations to evaluate this integral. So using the parametrization with the square root, where x is equal to the parameter. Then, yeah, we will prepare the differentials. Dx is dt, and dy is the derivative of this function times dt. So we have minus, and the derivative of square root is 1 over 2 times the square root, 2t minus t squared. And this is a composite function, so we must multiply by the derivative of the inner function, which is 2 minus 2t. Yeah, and now we can write the integral. And t runs from 0 to 2. f1, which is x, which is t, times dx, which is 1 times dt. We will write dt at the very end, plus f2, which is xy, x is t, y is minus square root, so we write minus square root of 2t minus t squared, dy, which is here, so minus minus gives again plus, and we can factor out 2, and we have, we can leave it as it is, 2 minus 2t, yeah, still we can reduce 2, and we have 1 minus t square root of 2t minus t squared dt. Yeah, let me check this with my previous computation. Yeah, now we can reduce this square root, and we get t plus t minus t squared. So the antiderivative is 2t integrated is t squared minus t cubed third from 0 to 2 is 4 minus 8/3, which is 4/3. Yeah. So we want to remember this result because we want to compare this with the computation using the parametrization denoted here by B and by C. Now, for the parametrization, for the second possible parametrization, B, we will prepare dx, which will be minus sine of t dt, and dy, which will be cosine of t dt. So the integral is integral from pi to 2 pi f1, which is x, which is 1 plus cosine of t, times dx, which is minus sine of t, and we will write dt at the very end, plus f2, which is xy, which is 1 plus cosine of t, times sine of t, times dy, which is cosine of t dt, yeah, and we want to integrate this. So we have integral from pi to 2 pi, and when we simplify this a little, we have here, if we expand this multiplication, then we have minus sine, let's like just ask for sine, minus cosine times sine, plus cosine squared sine, plus, cosine sine, plus cosine squared sine. Cosine times sine is minus, cosine times sine is plus, these terms cancel, and we can factor out sine. And we have cosine squared minus 1 dt. And to evaluate this definite integral, we can use substitution for cosine, say u, then minus sine t dt is du, and we have integral when t starts at pi, cosine starts at minus 1, and when t goes up to 2 pi, then u goes up to 1. This is easy to illustrate with the following graph of the function cosine. We start here and we go up to here. T runs from pi to 2 pi and u runs from minus 1 to 1. Then sine t dt is the differential of the new variable up to the minus sign. So we swap this and we are done. And we have 1 minus, and cosine is u. Then the antiderivative is u, well, yeah, and we can take 2 times integral from 0 to 1. because 1 minus u squared is an even function, and when integrated over a symmetrical interval, we can multiply by 2 and taking only from 0 to 1. Then the antiderivative is u minus u cubed third from 0 to 1, which is 1 minus 1 third, which is 2 thirds, times 2 is 4 thirds. In perfect agreement with our previous computation. This illustrates that when changing the parametrization, even for a non-conservative vector field, this is not important whether the vector field has potential or not. So for any vector field, for any line integral, if you change the parametrization, keeping the same curve, keeping the same path, absolutely the same, not just the initial point and end point, absolutely the same, will not change the result. Well, and what about the third parametrization? So in the case C, when x is fraction 2 divided by 1 plus t squared, and y is 2t divided by 1 plus t squared, and t goes from... we didn't write the limits. In this case, t starts at minus infinity and goes up to 0. If t starts at minus infinity, then x starts at 2 over infinity, which is 0. And when t goes to 0, then at 0, we have 2 divided by 1, which is 2. If we take the closed interval from the right. And y, if t starts at minus infinity, we have small infinity divided by large infinity, which is again 0. And for t is 0, y is 0. So the initial point is at the origin, and the end point is the point 2, 0. And in between, y is negative because t is negative and 1 plus t squared is positive. There is one small difference between this third parametrization and the previous two cases. Can you see it? If you consider real values of the parameter, then it may go to minus infinity, but t will never be equal to minus infinity. So actually, the point 0, 0, the origin, is not achieved, so we should write the curve like that. The origin actually does not belong to the curve described by this parametrization. But for the purposes of the line integral, this one point is not important. Then we will need the differentials. Derivative of this is 1 plus t squared to minus 1, so we have minus 1. 2 can be written in front of the fraction, 1 plus t squared, square of that, times the derivative of the inner function, which is 2t. And for y, we have to differentiate as a fraction, so we put 2 in front of the fraction, and we have 1 plus t squared, square of that, and derivative of t is 1 times 1 plus t squared minus t times 2t. dt if we write the differentials. Well, so we have all we need to write the integral. So using this third parametrization, the integral will be t goes from minus infinity to 0. And we have f1, which is x, which is 2 divided by 1 plus t squared, times dx, which is minus 2, times 2t divided by 1 plus t squared, square, and we will write dt at the very end. Plus f2, which is xy, which is 2 divided by 1 plus t squared, times 2t divided by 1 plus t squared, dy, which is 2 times, now 1 plus t squared, square of that, and here we have 1 minus t squared. And dt. Well, we can simplify this a little. We can bring these two terms to a common denominator, which is 1 plus t squared to the power of 4. Because here we have 1 plus 2 is 4. But here we have only 1 plus 2 is 3. So we must multiply this by 1 plus t squared. We can factor out minus 8 and minus 8 is out, and we have t times 1 plus t squared. We have factored out minus 8, so 2 is out, and when minus, then this is t squared minus 1, and we have plus t times t squared minus 1. Is it so? T times 1 minus t squared minus 8 t times t squared minus 1 plus t times 1 plus t squared, okay. Yeah. And this numerator can be simplified to, here we have t plus t cubed plus t cubed minus t. So t minus t cancel, and we have two t cubed, and 2t cubed can be written as 2t squared, because now it's a good idea to introduce a substitution for 1 plus t squared. Say that. then 2t dt is dz, and we have minus 8 integral. When t goes to minus infinity, then z goes to plus infinity, and when t goes to 0, then z goes to 1. Well, you may notice that here the integration limits go up. Here you go down from infinity to 1. The reason is that the coefficient that relates the change of t and the change of z is 2t, and for negative t, this is negative. So positive change of t results in negative change of z. And then 2t dt is dz, and what remains is t squared, which is z minus 1, divided by z to 4. But this is easy to evaluate. This is infinity 1. Z divided by z to 4 is z to minus 3 minus z to minus 4 dz. Well, to be more precise, if the limit is plus or minus infinity, this is an improper integral, and we should integral from some a and consider the limit for a going to infinity. But as a abuse of notation, for the purpose of short writing, let me write just this infinity as a shorthand for the limit. But the antiderivative is easy to find. This is z2 minus 2 divided by minus 2 plus z2 minus 3 divided by minus 3, which gives plus from infinity to 1. And z to minus 2 and z to minus 3 at infinity is 0. More precisely, the limit for z going to infinity is 0. And when evaluated at 1, we have minus 8 times minus 1 over 2 plus 1 over 3. Which is 8 times 1/2 minus 1/3. And 1/2 minus 1/3 is 1 over 6, which is 4 over 3. 4 over 3, remember? The same result that we obtained using the first and the second parametrization. So this exercise illustrates that if we keep the same line, keep the same path, but change the parametrization, actually changing the speed we travel along the curve does not change the result of the line integral.